Welcome to video two of B04, our introduction to Python. And here we're going to look at why we want to learn to code in Python. In video three, we'll look at further details on setting up the Python environment. So our main motivation is that is very, very common. And a lot of the underlying tools that we use in bioinformatics use Python. So it's good to know how programs are written and to align our approaches with existing tools. It's a very general purpose language. You can run jobs with it. You can manipulate data. You can visualize data. It has a reasonable development speed and enables good practices as well. And you'll find that the PyCharm prompt that we're using will actually kind of give you guidance on how best to structure your code. It's very portable, which is important with research and aligning with fair data principles, and has many, many useful features. So we want to kind of consider other areas of science and really develop the area of biology that has really not developed very much in its computational competencies. So we want to be part of that future where we're creating opportunities for our colleagues, for ourselves, and for better research in this wider area using computational approaches that complement existing approaches in the lab. So Python is very, very handy. It's very commonly used for scripting and tool creation, just like R or many other languages. It can operate as a sort of a container or a wrapper for other languages too, in the same way that they can for Python too. It can be very, very basics or advanced as well. It's different from R in the sense you have to compile scripts that you write often. So that's a slight different. It's free, which is great if you're working in different labs or environments, and has many capabilities as well. What is the best language? Well, that's really very hard to say. I've used many different languages, and they all have different features and different advantages and limitations. And there's not so much a hierarchy between them, but it's more like the classic analogy is your favorite topping on a pizza. Everyone has a different suggestion, and all are equally valid. So Python originated from the APC language in 1987. I think it was developed fully by 1989. It was actually developed mainly by one person, Guido von Rossum, who kind of hung up his coding fingertips in 2018 and is developed by others since. It gradually increased in popularity during this time. The Python 2 was first developed in 2000, and Python 3 has been developed since 2008 and is the existing version. I think 3.11 is the most recent major release. However, some of your systems, you might find that you're running 3.9, which is what the Chorus cluster use, which is perfectly fine as well. So we want to learn to code because the volume of data that's being produced has dramatically increased over the past few years and is likely to continue to increase. You see that increase in recent years is roughly comparable to Moore's law, which reflects the numbers of transistors that can fit on a computer chip, and Moore predicted that would have a doubling time of about 2 years. And we see that sequencing technology had a big jump in the 2007, 8, 9, where it was in excess of Moore's law, but has since kind of become more comparable to it. So we can at least assume that the volume of data that we're dealing with in 2 years' time will double, and in 4 year times will be considerably larger as well. And we need to have the computational skills to deal with this. So why learn to code? If you go further back, you can see that this rate of exponential increase was present even well before bioinformatics was even formalized as a proper research area. It can be a key part of our experimental analysis. And if we think about this in the same way that we have to design other experiments, we should think about a design for our experiments that link to code, our setup, what data are we using? Is the data clean? Have we done QC on our data, which is very important? Can we manipulate it into a form that makes sense for our analysis? And a lot of this, the raw data QC, tidy data manipulation is a lot of work. Can we summarize our data and then get results from that? So you can think of these stages and a framework around those stages, whether you're writing in Python or any other language, it will help you. So you should learn to code because you'll typically need to do things many, many times, and you'll find that when you're writing a script, you're writing the initial versions, the ancestral lines of code that will create your final masterpiece. So a lot of the time you're writing and thinking and modifying and rewriting and thinking, a bit like writing a Word document or a paper. Sure, your first draft of your paper is really important to just get words on a page. But just like with coding, you often find that have several different drafts before you get to your final manuscript that you're happy with. Sorry, I forgot this part. And most importantly, you can recycle your code. And that's really, really handy, especially if you're kind of struggling to know where to start with. So the advantages are obvious. You can track how each result was produced, avoid manual manipulation steps. Your versions control of your scripts and your tools used. You can store intermediate results or have interim results as you go along. You don't manipulate the raw data. And importantly, you should try to comment on your code in detail to explain what you're doing. So this will mean that you will find that you have initially a myopic picture of what's going on, but learning to code will mean that you can think further about what you could do. It will take a lot of learning, but at the end of it, you'll find that you're much more capable as a scientist to take on new areas. And you can share that knowledge with others, which I really encourage you to do. So in our next video, we'll look at setting up our Python environment. So please look at that video 3 next.